And we're here at Lucid in California to talk to some of their chief engineers about their technology and what they're doing with their new launch on the Gravity. Hi, welcome to Munro Live. I'm Paul Turnbull, lead engineer at Munro Associates. Before that, I was with General Motors in the role of technical specialist for electric machine development, and prior to that, at Ford in the same role. I'm here today at Lucid talking with James Hawkins, Senior Director of Engineering.
Hello, I'm James Hawkins, Senior Director of Engineering at Lucid. I started here about 9 years ago this week, and I started in the chassis and suspension team doing structural engineering, designed parts of this car we hear, the Lucid Air, and then I moved on after a couple of years into the battery team and high voltage, and now I am responsible for the chief engineering team, advanced engineering, and a few other functions here at Lucid. So what we're going to talk about today is the Lucid Air.
Efficiency. And where does it all start?
Yeah, that's a great question. So for me, it does all start with efficiency with the Lucid Air and with Lucid in general. The Air is our first vehicle. Efficiency is something that we should all care more about. And efficiency isn't just one component. Often the powertrain, the battery, they get a lot of credit for the efficiency of the vehicle, but actually the number one contributor to efficiency is aerodynamics. Now, we can't just look at one thing for efficiency, it is the entire system. And so we're going to go through a few areas on the vehicle that contribute to the efficiency of the car. And we're going to talk a bit about why efficiency matters to our customers and, of course, to the world. So the whole car is pushing to achieve the lowest coefficient of drag we possibly can. Aerodynamic efficiency is a function of CDA, CD being the coefficient of drag, which is actually a mathematical description of the shape of the car, or a shape of anything, its ability to flow through the air. What we do is we take that descriptor and we multiply it by the frontal area. So a bar of soap or a Lucid Air, if they were exactly the same shape, would have the same CD, but of course a very different frontal area. So we multiply it by the frontal area to give us how much drag this car will have when it goes through the air. And everything you see, every shape, the shape of every A surface, as well as those that we can't see, which we'll talk a bit about, contribute to that CD. I'm very proud to say that the Lucid Air has a very, very low CD, one of the lowest in the industry, I believe the lowest in the industry, and it's 0.197, I believe, for the Lucid Air Pure. And that's really a result of fastidious attention to detail from every engineering team at Lucid, driven by our world-leading aerodynamics team. A couple of examples that I'd love to give you guys about some of the features that we put into this car to make it special from an aerodynamics perspective. One is that you can see, as you pointed out, we've got some interesting features on the front here. This is actually a real air duct through here, which does a number of things, one of which actually cools the headlights, but it also bleeds pressure from the high area in the front of the car. We get stagnation of air at the front at speed. But also we have them on the side here. This is an aerofoil section, and actually at highway speeds generates thrust. So that takes high pressure air away from the front and generates thrust with an aerofoil section. So it's little things like this. They don't make a huge difference, but every little bit counts. And when you add them up, then of course it makes a compelling difference. Another thing I want to talk about aerodynamics is something I'm very proud of. I was responsible for the battery team here at Lucid from around 2017 onwards. And the battery itself, we can talk more about the battery when we look at the skateboard, but the battery itself isn't flat. It's very easy on an EV to make a flat battery. Batteries want to be stacked with modules typically and want to be a nice straight line. Mm-hmm. But the battery on the Lucid Air is not flat, it's actually curved. It creates an airfoil section for the entire vehicle. The car is actually a wing car. Now, if we look underneath the Lucid Air, there's not a single bolt head protruding. Everything is flush and smooth. so that we aid that aerodynamic
So the air that you don't see under the car is also being sculpted.
From my perspective, it's even more exciting than what's on top. To show you an example of this, at the rear of the car, there's a diffuser. And you see this on a lot of vehicles, internal combustion engines or electric alike. And there's a diffuser here, which is responsible, along with the profile of the upper side of the car, to create the flow of the air as it leaves the back of the car. It has a lot of responsibility for stability at speed, the actual diffuser. And if you have a flat battery, it comes flat all the way to approximately where the rear axle is. And then you end up with a very steep diffuser, which can have a lot of aerodynamic drag. We actually start our diffuser just in line with the B-pillar. So the battery pack itself is the diffuser from around the B-pillar all the way back to the rear fascia. And so by lengthening that, we can have the same aerodynamic performance in terms of stability at speed, but with a lower drag coefficient.
So it's as much about how you put the air back together at the back end of the vehicle as it is how you're parting the air as you drive through.
Absolutely right. Yeah.
Fantastic.
So if we talk about efficiency, the number one contributor to efficiency, like we said, is aerodynamics. But it's every little thing, and I would love to talk more about that. If we consider that aerodynamic efficiency is CDA. CD, we can talk about CD for hours. The flush door handles and everything is in line, as you mentioned before. But the A, if we can diminish the frontal area of the car for a given user experience, then we must benefit the efficiency.
Which is impressive because as I drove it, the air has a lot of room on the inside. Right. It feels like a spacious vehicle, and yet you've done that with a smaller frontal area than your competitors.
That's exactly the point. So if we can focus on packaging of the car, for a given interior occupant space, we can create a smaller exterior frontal area of the car. And of course, that doesn't just help aerodynamics, that also helps the drivability, usability, parking in tight spaces, particularly in Europe where we have multi-story car parks, etc., which are very narrow entrance and exits, and just town driving as well. If we can make the car smaller on the outside for a given interior space, then we can improve our customer experience and efficiency, range, etc., etc., etc. Typically with Lucid, we are about one segment smaller, one size smaller for a given segment. So this is, the interior is the same size as a full-size sedan, a long wheelbase 7 Series, for instance, but one size smaller than that, a sort of mid-size sedan on the outside.
Excellent. Now that becomes a real challenge when you go to something like you're launching now with the Lucid Gravity, trying to fit 3 rows of seating into a space and keep that small frontal area.
Well, exactly that. And the Gravity is an exceptional example of that same theory, that same thinking with the packaging.
We're just going to walk over to have a quick look at the Gravity. And for some of our viewers, this might be their first look at the Lucid Gravity.
So this is, on the interior, a full-size third-row SUV, but on the outside is one size smaller in that same segment, so that we can generate the same efficiency story. And actually, you can see that it's not a very tall vehicle, but inside it's a very spacious cabin with a full-size third row that you and I could comfortably sit in that third row.
Yeah, some of the third-row seats are cramped even for children. And it's real refreshing to just be able to fit a real person into the back seat.
This is a very exciting product, and I'm really proud of this, and I'm very, very excited for people to experience this at the end of the year.
Fantastic. And I'm sure that as a director of engineering, there's all kinds of challenges that are occurring during launch, and I'm going to want to talk to Eric about some of that stuff.
So I'd love to show you guys some of the features on the skateboard.
Yeah, let's have a look.
Some of the ways that we've managed to miniaturize the things that customers have to have in their car, like a powertrain, like a battery, but don't necessarily add value to their everyday experience from a packaging perspective. So, if one of the tools in our toolbox is that we are a vertically integrated company. So that means that we all of the design engineers for all of the components sit within Lucid. It's our own technology. We do not rely broadly on a supply base for doing the engineering of the components that really matter to this, that really generate differentiation for this car in the market. We try to control all of that ourselves. And that includes the battery packs, it includes the powertrain, the motors, the suspension design, the body structural design, all of the chassis design, all of the crash simulation, aerodynamics, everything is done in-house. All of our simulation is done by ourselves, and that's simulation for aerodynamics for crash, but also things like electromagnetics in the powertrain. And I know you're going to talk to Emad later. He'll love to talk to you more about the simulation work that's done in the powertrain.
I've got some great questions for him and about the electromagnetics, which are groundbreaking. Certainly one of the keys to that amazing efficiency, and again on the Air Pure 5 miles per kilowatt hour, very impressive accomplishment on real drive cycles.
And it doesn't stop there. It's not a target for us. It's just a milestone along the way. We are going to continuously, fastidiously pursue efficiency. And one of the reasons we care about efficiency, of course, is that if a customer would like a car that goes a certain range, let's say a customer knows they want a car that can drive 400 miles. Well, there aren't very many cars in the world that can drive 400 miles, EVs, that can drive 400 miles on a single charge. But let's say we have one. The more efficient we can make our car, the fewer batteries we need to drive 400 miles. That means that it's lighter.
It's a cost savings for the customer, right?
Well, absolutely. Well, at the end of the day, it's cost savings for the customer. But more than that, it's a cost savings for all of us because, of course, it requires fewer minerals, fewer materials going into that car. It's compelling if we look at the benevolent cycle of efficiency. Let's say we find a technology that makes it a little bit more efficient. Let's say we found a new aerodynamic enabler that increases our efficiency. That means for that 400-mile car, we can put fewer batteries in. Fewer batteries makes it, yes, cheaper, but also lighter. A lighter car uses less energy to go a certain distance. So suddenly it becomes more efficient. And we engage in this benevolent cycle. We want to ride that wave as far as we possibly can in the name of efficiency, and in the name of using the fewer batteries as we possibly can to go a certain distance.
And here, the effect you were talking about with sculpting of the battery tray, it's so subtle that if you didn't tell me about it before, I wouldn't notice it.
Absolutely.
But now you can see that the floor of the battery actually
it's very, very subtle. And of course, the point is, it's only a small number in terms of the dimension which it changes as it goes backwards, but it's over a large area. So of course, the force that can generate, or even a small pressure change over a large area, is a large force.
And so then the rear drive unit, which is now sitting up a little bit to allow that aero underneath. And
that's right. So when we designed the car, the aerodynamic surface underneath was our datum. We couldn't violate that because that generates the efficiency of the car. So everything in the rear end of the car is designed around that diffuser as a datum that we must respect. And so the powertrain is placed exactly where it should be. The subframe is designed as such so that it follows the line of the diffuser. Every millimeter has been counted for. Every millimeter does something in the car. Every ounce, every joule of energy. And the funny thing is that it's easy to look at this and go, well, I don't believe you. There's a big space here. I can put my fist in here. Well, the thing is that the rear powertrain was designed, the rear subframe was designed to accept the twin motor. So this is only the small motor in this car. The Lucid Air Sapphire has 2 motors in here, which of course is larger. And as such, it fills all this space up. So every millimeter is counted for on one or other of the variants.
Fantastic. And yet there's still space for a spacious trunk and this crash protection for the occupants.
That's right.
Crush space here.
Yep.
To allow for in the roller skate safety as well as space.
Absolutely. So we can't compromise on safety. It has the highest safety standards, of course. These are the crash rails here. They actually crush during a rear impact. This is the sub-trunk, so all this space here is usable for the occupant. And these are the rails that crush. And then here we have a large casting. This is the rear torque box, one on each side. and it's closed off with a stamp panel. So this car, the body structure of this car is made using castings, stampings, and extrusions, all in harmony. It's bonded, riveted, and screwed together. And of course, the adhesive does the majority of the structural work when it's operating under its normal conditions. I'm often asked about spot welds versus adhesive, and it's a really interesting discussion. Spot welds, of course, are much more common on steel body structures. Mm-hmm. It's possible on aluminium. But if you imagine it's similar to, if you have an adhesive, you have a continuous bond, a continuous join. It's like a zipper versus a button. So a spot weld will just be a discrete joining point along a panel. And of course, adhesive is a continuous join. We get to really benefit from creating beautiful, efficient structures that are stiff and strong in the event of a crash. And then we have, of course, these discrete points here, which are the flow drill screws. And we also have self-piercing rivets that hold the body structure together, which you can see on the side flange here. And these act as curing aids. So when we put the vehicle in our curing ovens, as the adhesive cures, those hold it in place. But also, in the event of a collision, they act as peel stoppers to prevent the panels from peeling apart. The weakness of adhesive is peel. Peel is the #1 failure mode for adhesives. So going back to the efficiency story, if I may for a moment. Going back to the efficiency story, we can see how small the powertrain is. And we're going to talk more about powertrains, I expect, in a moment. What's really important for us is power density. So we want to look at every aspect that can aid our efficiency journey. The smaller we can make the powertrain for a given power, let's say we want a 200, 300, 400 horsepower powertrain, the smaller we can make it for a given power, the fewer materials we are able to use, the lighter it can be, and the cheaper it can be.
Right.
Powertrain cost is dominated by materials. And inside the powertrain, there's no special materials. It's iron, it's copper, magnetic materials, permanent magnet motor. But if we can use smaller volume of those materials, of course, it becomes lighter, it becomes cheaper.
And that drives
for a given power.
That drives a thermodynamic problem, because now you have the same amount of power in a smaller space, and so you have to have an innovative way to get the heat out.
Exactly that. And of course, going back to our vertical integration, everything is designed and simulated in-house so that we can iterate very rapidly and generate what is the most optimized solution to that problem. Now, this is the rear powertrain. It's almost identical unit on the front, but it's actually standing in a different orientation. It's standing upwards. So you can see this here. This is the inverter. That's the power electronics.
I like the black box. It's the brains of the powertrain, and making the styling of it a black box. And actually, one of the things that Lucid, I think, doesn't get the credit for that they deserve is their the development of controls. A huge enabler for the kind of efficiency you're talking about are in the motor controls. And delivering that torque to the road in a way that doesn't make the wheels slip.
Absolutely.
And that's something that Lucid right now is a world leader on.
I couldn't agree more. To your point about the vehicle being a system, everything matters. The efficiency is the entire system. It's no one component, it's no one system, it's no one team. But the controls team do an exemplary job of not only running this in an efficient way, but in a very performant way, but also one that is safe and provides exceptional control, traction control in low mu handling conditions, as well as when you really want to be playful.
So a vehicle like this, 2 motors, a large battery, long range, it ends up, and it's a fabulous luxury vehicle, but is there a plan to make this kind of technology more accessible at a lower price point for other customers?
Absolutely. And so within Lucid ourselves, of course, we have a roadmap for future vehicles. On that roadmap is a newly announced mid-size version of the Lucid car. So that absolutely will be a lower cost version of the vehicle, much higher volume. But also we license and sell our technology to third parties. So there's an agreement with Aston Martin that we have for future powertrains, which is public. And of course, we continue to strive towards building other relationships with the OEMs. Anyone who would like to use Lucid technology in their cars, we'd be very willing to talk to them.
That's a good idea. It may be a way for other companies to get jump start into where you guys are at the front.
So one more word on the powertrain. This is, of course, the inverter on the top, and underneath is a motor gearbox. It's a permanent magnet motor and a complete reduction gear set. And we'll talk a little bit about why it's special. You've done some teardown on your channel already, which is very good. And we'll see what makes the Lucid powertrain so special on the inside, how it's so small, how it's so power dense. And we'll talk about some of the numbers.
So thanks for bringing up the aerodynamics, but what about the front of the vehicle that makes it so aerodynamic?
Yeah, I'm glad you brought it up. The front of the car is actually very special. It looks trivial. It looks easy to design the front of a car, but this is a very feature-dense area of the vehicle. Now, behind here is a large crash rail, which is largely non-negotiable, the bumper beam itself. And of course, that is there for the safety of our occupants and is defined by a lot of standards and specifications that we have to follow. Typically, you'll see at the front of a car, there's a great big radiator here for cooling, big cooling pack for AC and for keeping the internal combustion engine cool. Of course, we have to deal with a lot less heat than an internal combustion engine does. Internal combustion engine will throw away maybe 70% of the fuel we put in the tank will just go as heat out of the exhaust pipes and out of the hood. And of course, cooled by that gigantic radiator that they have in the front. We don't have such a big problem, much higher efficiency of an electric vehicle, but we still have to reject heat. Of course we have to, and we still want air conditioning, so there's still a condenser. What we've done is we've taken this challenge and through the vertical integration, designing everything and simulating everything ourselves, we've come up with quite a clever solution. The radiators actually sit in front of the front wheels, and we can see that more on the skateboard over there. Maybe we can do that in a moment. But there's a radiator on each side for cooling the powertrains, and a condenser for the air conditioning on each side. The thing is that when you're driving along at freeway speeds, you have a lot of air stagnation at the front, an area of high pressure buildup. And we want to try and bleed that away. And that's done on an internal combustion engine car by moving it through the fascia, through the radiator, and then out of the car, through the engine bay. In the front of the Lucid Air, we actually have a frunk. And of course, as soon as we put a radiator in the front of the car, then we lose space for the frunk. We lose the ability to generate value for our customers, that space that we all like to put our luggage in. So instead of doing that, we've put the radiators there, and we've overcome the challenge of moving air from this area of stagnation, turning corners into the front of the wheel wells by generating a twin vortex solution. So there's actually a vortex duct on the one here and one here behind the active grille shutters. And that takes air, turbulent air from the environment, puts it through the vortex, spins it and it generates and it increases in diameter as it goes through its path, which slows the air, turns it into a laminar flow, and then it exits over the entire surface area of the now much smaller radiator, because you can use it more efficiently and effectively. You can use the entire surface area of the radiator. Historically, you typically use only the center circle portion where the fan shroud is. So what it means is, on the front of the car, you can have a much smaller opening on each side. You can control it with an active grille shutter much more easily. You can gain the space back in the frunk, but maintain the standard of cooling and the performance of the cooling. It also means that we get to control the front lip of the car. We can give a lot more latitude to our design colleagues so that they can generate a much more aesthetically pleasing vehicle, but also the aerodynamics of it can be more compelling. Now at the front of this car, we've also got a LiDAR and long-range radar, and we've got our own headlamps that we generate in-house. Again, if we generate our own headlamps in-house, we can make a better product that's more performant, but also we can control the packaging and the size of those headlamps to bring this front fascia lip lower than it would otherwise be.
So you were talking about the vortex tubes that direct the air from the front of the vehicle around to those two radiators on the sides in front of the front wheels.
Yeah, that's right. So we can see it just here. This is the intake here with the active grille shutter, which opens and closes on the front. And then air enters into this duct here, which turns the air into a laminar flow, and then back through here over the radiators just in front of the front wheels. So we get to use this space that would have a big cooling pack in it. We get to use this now as frunk space for the occupant. And of course, it's not just the package volume of a radiator and a condenser, a cooling pack. It's also the space behind that to allow the air to flow out with the lowest possible resistance.
So you've summarized the philosophy of efficiency that's driving through into the construction and build of the Air. And how does that philosophy play out with the launch of the Gravity?
Well, yeah, it's great. Certainly, I think the Air has begun to really put in people's minds the importance of efficiency. And not all EVs are created the same. You know, it's possible to have a gas-guzzling EV. We see that in the market. The Gravity intends to absolutely continue what the Air started in terms of really striving for maximum efficiency. And the efficiency that we as engineers, we like to obsess over a certain particular feature, aspect, something that we designed. And that sometimes comes at the cost of the customer experience. I want to make sure that we put the customer and the customer experience at the very forefront of what we do. So why should efficiency matter to the customer is the question that we need to ask ourselves, and we have been asking ourselves through the development of the Gravity. So we certainly don't want efficiency to compromise what the customer's experience of the car is. So as we see with the Gravity, it's a full third-row SUV. I'm very excited for you guys to get your hands on one in the future and for our customers to drive them and tell us what they think. But certainly, it's been designed with an eye on their experience, on how we are responsible for creating an outstanding vehicle with unparalleled efficiency. Now, of course, there's a topic to be had about how you drive the car. I mean, we can all perhaps improve our driving habits to get efficiency, but we're going to do everything we can to generate efficiency and value for our customers.
So does that, I heard you mention that this not only ends up being an enabler or something for a great customer experience, but it also helps drive sustainability for the company.
Well, naturally, sustainability for the company, certainly. Sustainability for the product, I think, is more important. Sustainability because we all have a responsibility for how we use the Earth's resources. If we can educate, if we can use this as a tool to educate people on power, on energy, I think we as a human race trivialize power nowadays. You know, if we say, well, it's 200 horsepower, 300 horsepower, what does that actually mean? And I think one of the reasons is that we use different terms for power. We use different units. In the home, we use watts and kilowatts, and in cars, we typically use horsepower. And you know how the two relate to one another. Well, they're about 3/4. So it's about 0.746 kilowatts in a horsepower. And if we were to try and put that into the everyday parley, we'll say, well, you know, we're all very responsible when we leave our homes and we turn the lights off because we want to save energy. And that's a very valid reason to turn your lights off, and it's very important to do so. But of course, then we get onto the freeway and we give a 0 to 60 run of our car, and we've undone 2 years worth of turning your lights off. The power levels are non-trivial when you start talking about cars. And so if we can improve the efficiency of the automobile, we generate distinct value when we start looking at how many light bulbs you turned off, for instance.
So it has a bigger impact than just a single car.
For sure, absolutely. And of course, if we multiply that by the number of people who we would like to adopt, not just EVs, but Lucid specifically, if you really want to make an impact on efficiency and the footprint that you have from an energy perspective in the world, then we get to make a real difference in the US and, of course, worldwide.
I think that's one of the things that drives us in this industry is the fact that we are now in the midst of a transition to a more sustainable economy, and making cars that are as efficient as we can make them.
Yeah, absolutely. And of course,
a huge way to help.
We have a responsibility for things like the load on the grid. You know, the electrification of the automobile isn't the only challenge. If everyone bought an automobile that is electric, it just pushes challenge to other areas of the infrastructure. And so if we can do so with the most efficient possible car, then we lessen the burden on the infrastructure. We can accelerate the adoption of EVs, and that's something really true to the core of what we're trying to do at Lucid.
Going farther for every kilowatt hour in your battery, absolutely. I mean, it translates into a faster charging time as well.
Well, it can do, and you know, I'm glad you brought up charging. Charging is so interesting and broadly misunderstood. I often hear how customers of EVs and of devices will say how quickly their device or their car charges from 20 to 80% or something. So we often talk about, I often hear how quickly a device or a car can charge from 20 to 80%. But what does 1 percentage point mean? 1 percentage point means different things for different devices, different cars, etc. If we look at cars, 1 percentage point in a large electric SUV that didn't pay much attention to the efficiency of that vehicle is dramatically different to 1% in the Lucid Air Pure, where we strive for efficiency and recently achieved a 5 miles per kilowatt hour EPA rating.
So maybe we should be thinking of miles per kilowatt hour, and that is actually one of the statistics that the EPA will put right on the sticker.
It is miles per kilowatt hour, so 5 miles per kilowatt hour for the Lucid Air Pure. But in terms of charging, maybe miles per minute. How many miles can I put on my car? How do I, again, to this point about customer experience, we as engineers want to fixate about percentage points, but actually what matters to the customer is how many miles per minute I can put on. I've got 5 minutes to stop and get a drink, change the diaper on my baby, I don't know. How many miles can I put on my car in that time? That's what actually matters. When do I get to leave before I know that I can make it to my destination?
That's real customer enabler. As an EV owner myself, as we're on the road, we're constantly making that calculation. How long do I have to charge to make it to the next
Is it
point?
a Lucid?
No.
Ah, well, you see.
Yeah, I could do better.
So I'd like to say that the Lucid is a great car and it's available. And we can take you to the studio down the road if you'd like. It's no problem at all.
Hi, I want to thank Lucid for providing us with this Lucid Air Touring to use while we were here. And it's been great because I've had a chance to get behind the wheel. And I have to say that several reviewers have called this the best luxury sedan ever made. And it's easy to see why when you've been driving it a little bit through the twisty canyons out here. It performs amazingly. But if you want a great luxury electric vehicle, then this one fits the bill. Thanks a lot.